Hi guys, good evening. How are you all? So I see that it's been a long time we had our last session. Our last session was on atomic structure. We are continuing our 11th standard chemistry. We have started it from mole concept, then after we took atomic structure. Our third chapter is redox reactions, and here we have the sequence. Here is the sequence of all the complete chapter what we are going to cover topic wise. Introduction to redox, then we'll come to what is the concept of oxidation number and oxidation state, type of redox reactions, balancing of the redox reaction. We'll go to N factor calculation and equivalent concept, redox reactions and titrations, and also some of the applications of redox reaction as in electrochemistry. And lastly, we'll do some of the JEE Main Advanced PYQ inbuilt inside this lecture. It's a total complete conceptual and theoretical lecture. Right after this chapter completion or this lecture, I will cover one more interesting lecture on all the PYQs from 2002 to 2024 of JEE Main and Advanced in redox reaction. That is what we are going to cover in our upcoming session. Am I audible, everybody? Am I audible to all? One more interesting lecture on. Absolutely. Thank you. So let us start our chapter. Before going to this chapter flow, I would like to ask you people, and I would like to take the benefit of this All India Mock Test IIT JEE 2025, which we are going to conduct, is going to happen next on 12th of January 2025, where you can give the test, take the idea of how the JEE Main exam is going to appear in your first attempt. And also apart from that, you also can enroll and can check the live rank predictor. We have this All India rank predictor over here. Link of everything of your AIMT and your rank predictor is given in the description. Go right now, enroll it, and you can give your best out of it. Yeah. Now let us start our chapter. Redox in real life. So first of all, we will know what is redox reaction and how redox reactions are seen in our daily to daily life. So you might have seen the combustion of any fuel, let us say carbon in presence of oxygen produces CO2. Sorry. This reaction involves two parts. The one part is carbon, which is converting into CO2, is called as oxidation. The another part from oxygen converting to CO2 is called as reduction. All the reactions in which oxidation and reduction occur simultaneously at the same time are called as redox reaction. Now take one more example. There is one more example, cellular respiration, in which ultimate source of an energy in human being encompass a series of redox reaction. Take a beautiful example, everybody. What reaction happens in respiration? It's the opposite reaction. What we should call it, like glucose and fructose. Okay, so we have sucrose here, C12, H32, O11 plus oxygen gives you C6H12O6 plus C6H12O6. These are glucose and fructose, and in order to balance it, 6 molecules of oxygen are used here, and this is a complete balanced reaction. So this reaction is actually telling us that some of the component of this group are undergoing oxidation and some of the component are going reduction, but this is a sort of reaction that occurs in the cellular respiration. This process is called as respiration. And then we have one more reaction that basically this is something that might not be of your interest, and you might have not seen this thing. Hopefully this is something that happens when someone with an alcohol limit beyond the driving level is basically considered, and that has been measured using this device called as breath analyzer. And what actually happens over there, guys, there is a chemical substance called as ethanol present in the alcoholic beverages that has been consumed by some person, and that undergoes in presence of permanganate ion as an oxidizing agent, which oxidizes this molecule to CH3COH, which is ethanoic acid, and using this reaction they somehow calculate the amount of the vapors formed, and they conclude how much amount of alcohol has been consumed by some person. So anyways, these all are the examples of daily to daily life where redox reactions can be seen. Now we all must know what is the exact meaning of redox in the terms of chemistry. We have the first definition of redox, that is red plus ox. So this is what we are talking about. Red stands for reduction and ox stands for oxidation. A reduction and oxidation individual are two different processes, but they both occur simultaneously whenever any redox reaction occur. So you must say that none of the process of oxidation or reduction occur individually or at first. They both happen together, and that too simultaneously means at same time. So that is what we call as the redox reaction. Here is the definition, what I have explained right now. Hopefully we all are aligned on the same page. We all are getting what I'm trying to explain. Now, if we go to the previous concept or the older concept that was considered while giving the definitions of reduction and oxidation, a classical concept is actually some older concept. So what does it say? Let me give you the idea, but anyways we are not gonna to learn this concept and we are not gonna to implement or apply this concept. We always be taking modern concept in the application part, but still just take the idea. Whenever a substance, any oxygen is added to some substance, the process becomes oxidation. So what we can say, simply addition of oxygen as one of the definition. So who is gonna to get oxidized? To whoever we are adding the oxygen. So let's say this is been added to this carbon. So this carbon going to COH is actually undergoing oxidation. You might be wondering like how I chose this carbon getting oxidized, but still take the idea of all the basic concepts, and then in application part I'll explain you how do you apply the modern concept and then get out of this concept of oxidation very easily. This might be a difficult concept right now, that addition of oxygen to this carbon is yielding it getting COH from CHO. So this is addition of oxygen, which is called as oxidation. Give me a sec. हेलो, एक बार वीडियो देखो यार, सबसे चल रहा था, क्या हो गया देखो ना यार वीडियो में. So guys, am I not properly visible? So guys, am I not properly visible? So guys, am I not properly visible? So guys, I think now we are properly connected. So guys, I think now we are getting. So now let us come back to our topic that we were saying. Addition of oxygen is called as oxidation. Addition of an electronegative substance. Addition electronegative substance. This electronegative substance or electronegative element will definitely be non-metal. Something which is connected with the non-metals will be considered to have the undergoing the process of oxidation. So this process, what we see, beryllium, since this is your electronegative substance, this is electropositive substance, which is metal, this is non-metal. So beryllium undergoing oxidation here. The very next is removal of hydrogen. So somewhere which you are seeing the removal of hydrogen occurring. hydrogen H element. So we can see from HCl, hydrogen is eliminated out forming Cl2. This process will be called as an oxidation process. And then again over here, an electropositive element which is sodium, which is being removed from NaI. This process will be called as oxidation. And now this is nothing but the removal of electropositive element. And who are the electropositive elements? Metals. So this is the older concept of oxidation and reduction that was used earlier. Nowadays we do not predict any process as an oxidation or reduction using this process. However, we are just taking an idea what was the older concept. In the similar way, we also have reduction. Reduction could be defined in terms of addition of hydrogen first. To whom we are adding the hydrogen? Cl2. So Cl2, from Cl2 it is going HCl. This process will be called as reduction. So the very first definition becomes that addition of hydrogen. Okay, in any way, H2H, in either way. We have another, that addition of an electropositive element or metal. So this will be addition of electropositive element, and we all know all the electropositive elements. Relative electropositive element have to be found out. If we talk about metals and non-metals, all metals are generally electropositive elements, and here aluminium is working as electropositive element. Next is removal of electronegative element. Can you see that now we are removing Cl2, the remaining part will be Hg. So Hg over here, in this process is undergoing reduction. Similarly, this part was reduction. So what we are doing is that we are removal of electronegative element. Now tell me which one of them is the electronegative. Out of mercury and chlorine, this is electronegative. So once electronegative has been removed, the remaining part is Hg electropositive. So HgCl2, Hg is the removal of electronegative. Similarly, we also say it removal of oxygen. Just like initially we said addition of oxygen in oxidation, reduction will be the removal of oxygen. So removal of oxygen as an element. So now oxygen has been eliminated out. So the formation of H2O to H2 is the reduction process. So that is what we call it as the older or classical concept of redox reactions. Very good. Very good, Rohit and Shriram. You got the correct point from here. But again, we all found that this was absolutely boring. It's not very easy to predict out addition of this to that and blah blah blah. We have the best example over here to explain modern concept. The very one concept among them is called as electronic concept. Now take this idea, everybody. It's very easy to explain. Electronic concept of identifying oxidation and reduction. Okay, so it's very simple that A, oxidation is nothing but the removal of electron. Any substance that removes electron, whether it is an ion, whether it is a neutral substance, or whether it's an atom or a molecule. So oxidation is the removal of electrons. Then another is called as reduction. Reduction is called as addition of electrons. Removal of electron, and then we have addition of electrons. Okay, now take this idea, take this example, everybody. Copper 2 plus zinc produces zinc 2 plus copper. Can you identify this reaction? What is exactly happening here? So let us say that if I take this reaction individually, so how can something, this copper 2 plus, can go to Cu? Have you ever imagined that if something in positive charge has to go to a neutral state or to zero, somebody has acquired 2 electrons. That is why the charge 2 positive has converted to 0. So we are right now adding 2 electrons. Addition of electron becomes what? Reduction. The another one is zinc going to zinc 2 positive. How can some species acquire a positive charge? Only way to acquire the positive charge is to lose electron. It might have lost the exact same number of electron because this is a balanced chemical reaction and balanced chemical equation. So we will say it has lost 2 electrons, and thus it has lost 2 electron. It will be called as oxidation as per the modern concept of electronic theory. Is it clear to all of you, everybody? So that is very first part of modern concept called as electronic concept. Now I'll take you to one more example and one more method called as the ultimate method that all we have to use. This is called as oxidation number method. This is called as oxidation number method. How do you identify using oxidation number? So guys, it's very simple that a process is called as oxidation whenever there is an increase in the oxidation state of some element, compound, molecule, or whatever it is there. Oxidation is the increase in, this is called as increase, above arrow increase in oxidation number, and similarly reduction will be what? Decrease in oxidation number, like that. So I can take you to the same example and can explain you how do we define these oxidation state and oxidation number and all. So take the same idea that Cu2 positive when combined with the zinc produces Zn2 plus Cu, and now take this idea, everybody, that oxidation states of ions are the charges they are possessing. Just like Cu2 positive has +2 oxidation state, it has 0 oxidation state, it has +2 oxidation state, it has 0 because it's a neutral molecule, neutral atom, neutral element with no charge on it. You can find out the nature of the process. Somebody going from 2 positive to 0, oxidation state has been decreased. This process, this oxidation number decreases, thus this process is called as reduction. Now look at this, something is going from 0 to 2 positive, the oxidation number increases here, thus this reaction is called as oxidation. This half process is called as oxidation. And as I told you that none of the oxidation and reduction occurs independently, isolatedly, or what we say individually. They all happen in the same experiment or the same reaction simultaneously, and neither of them occurs first, all occurs exactly together. Now this process of finding the oxidation number is a task to us, because if we are very well known about how to find out the oxidation number, we can easily find out the nature of the process, whether it's an oxidation or reduction. So before going to the finding of oxidation number, oxidation state, let us solve some of the questions. So the very first question we have in front of us, hydrogen and chlorine are adding. The chlorine undergoes what? Guys, as you all know, addition of hydrogen to some substance and leading to some product is an example of reduction. But there's one more thing which we can do, that chlorine over here from 0 oxidation state going to -1, and then hydrogen from 0 going to +1, then we can say that chlorine is undergoing reduction and hydrogen is undergoing oxidation. So the correct answer should be B. Now you people might not be able right now to apply the concept of oxidation number, but just hold your patience. Allow me just half an hour and I will explain this oxidation number and this concept in very detail, because believe me, if you are studying redox reaction, the concept of oxidation number and oxidation state is highly important out of whole chapter. Let us come to one more example. If somebody is sending nitrogen to nitride ion, how nitrogen can be converted into nitride ion? Yes sir, definitely by acquiring 3 electrons. If something accepts 3 electron and absorbs or accepts electron, this process is called as reduction. If something from Cl minus is going to prepare Cl, so definitely this charge has been removed in terms of electron, and yes, this process is called as oxidation. So where this is reduction, this is oxidation, right? Absolutely right, sir. Now we'll start the very first and very important part of this chapter called as oxidation number. Guys, what do you think of oxidation number? First of all, we all must know what is the meaning of oxidation number. So, let me give you a definition of oxidation number, oxidation state. Oxidation state, okay. So basically oxidation state is the residual charge, the remaining charge, the residual charge left upon an atom when it is completely removed, from its combined state. Combined state could be an ion or a molecule. In such a way, किस तरह से? No, by breaking all bonds in such a way that the more electronegative element acquires all the shared pair of electrons, Now this definition might sound you a very huge part, or a very difficult even to understand, but believe me, using one example you can get this concept very easily. So I'll explain you the concept using one example. So what happens here, everybody? Let us take an example of HCl. We have hydrogen, we have chlorine. We all know that hydrogen is less electronegative. So first of all, there are 2 electrons here shared by these two, and we also know that hydrogen is less electronegative while chlorine is more electronegative. This more electronegative, we have to break this bond in such a way that more electronegative acquires the both electron. Now after acquiring these both electron, how much charge does it get after losing one? Positive 1, and this will require a negative 1. Overall molecule is neutral. Plus 1 and minus 1 are the residual charges. So you can simply write that oxidation state of hydrogen is what? Positive 1. And oxidation state of chlorine is what? Negative of 1. Is it understood to everybody? Is it understood the very basic example I told you? And I'll take you to some more difficult examples from here, but right now try to grab the concept first of all. There are so many shortcuts to find out oxidation number, and once you will come to know the shortcuts you want, you merely apply this process of breaking the bonds and all, but somewhere it will be very important, and this is the concept that never gives you an incorrect answer. It will always give the correct answer. So let us take few more examples. We all know HCl, in one covalent bond 2 electrons are shared. Let us say 1 electron is of hydrogen, another 1 electron is of chlorine. Both of the electrons are now taken by either of the element. So as many as number of bonds you are breaking, that much amount of charge you have to apply. On electropositive it will come in positive, on electronegative it will come in negative. So I'm breaking one bond, I will give it -1 charge, I will give it +1 charge. Is that easy? Take one more example, everybody. We have 2 bonds to break here. Hydrogen will acquire a +1 charge, being less electronegative. Oxygen being more electronegative, it will acquire -2 charge. Why? One from here, one from here. Similar way, Apply the concept to break these bonds. 1, 2, 3. This will be acquiring positive 1, positive 1, positive 1. This will be acquiring a negative 3. So that is how we apply the concept of oxidation number. And now I know that this is not pretty fast process as of now. Drawing the structure and then knowing everything, it is difficult as of now. But believe me, right after knowing some of the very important elements which carry usually the same kind of oxidation state, you will learn them, and then it will become very easy to find out the oxidation state of unknown element. We have rules to calculate oxidation state. So some rules we got to follow, we have to apply so that we can get the idea of oxidation states of many elements. Number 1 says that elements, if they are existing in their free state or in their elemental form, or not in just a combined or compound form, in that way they will be saying, they will be said to have oxidation state of 0. Let us take this idea. Let's say if I simply write it, let's say if I simply write it that iron, magnesium, helium, neon, argon, these are all monoatomic elements, and we have the oxidation state as 0, 0, 0, 0, 0, 0. It's very simple to explain. Now if we are taking H2, now try to observe this structure H2. So if you break them, both of them are equally electronegative. Only share 1 electron each. They only share 1 electron each. They do not distribute in such a way. That's why the oxidation state becomes what? 0, 0. None of them is giving the electron, none of them is taking the electron. Both of them are just sharing electron. Whoever had 1 electron in its outermost shell is acquiring that charge only, and that's why they are supposed to have this 0 oxidation state. So let it say O2, let it be O3, let it be whatever it is, P4, S8, etc. Everywhere, whenever the elemental form is there, the oxidation state will come up as 0, 0, 0 and 0. Please note this part down. It's very important part I'm explaining. Now, next point, if any ion is given and the ion is monoatomic, if an ion is a monoatomic, its charge itself will be considered as oxidation state. So see, this is Na positive, Mg positive, Cl negative. Let's say if N3 minus ion is there, the oxidation state becomes -3. If some oxide ion is there, then the oxidation state becomes -2. If some aluminium 3 plus ion is there, then the oxidation state becomes what? +3. But that is what it is applicable up to, only up to monoatomic ion. Not more than 1 atom must be there. Clear? Now, in case of polyatomic ion also will be discussed later, not right now, but will be discussed a bit like right after this. So we have another important element that we have to first accept, called as oxygen. So oxygen as an element can exist into so many states. Number 1, elemental state. What is the elemental state? In its reference state, or like in the one it exists freely, not in combined state from others. This will be O2 or O3. So there will be having an oxidation number of 0. In the all elemental state, we have oxidation state of 0. Very first case. Second case, let us say if oxygen is there in the form of oxide. This is called as oxide, or we call it normal oxide, and it look like this, O2 minus. Then its oxidation state will be coming what? Minus of 2. This is third, peroxide. What is a peroxide? O2 with 2 minus charge, or one oxygen with a negative 1 charge. So definitely the oxidation state will become what? -1, because oxidation state of one element, one atom we are writing. Let me give you some examples of oxide. Example: H2O, CO2. Wherever usually you see oxygen, it will be appearing in -2 as an oxide only. It's somewhere, mostly it is present in oxides only. So like iron oxide or carbonate ion, whatsoever is there. Majority, like 99%, you'll find its combined form in present of oxide form. Then another could be a peroxide. So in the case of peroxide, there could be several examples such as hydrogen peroxide. It is present in -1 state here. Sodium peroxide, Na2O2. We have barium peroxide, BaO2. Then like this, etc. Fourth is called as superoxide. Fourth is called as superoxide. So what is the superoxide? The superoxide is oxygen with a negative half charge or a molecule of O2 acquiring a -1 charge. And its examples are pretty limited. Examples are, so this will be having an oxidation state of what? Negative of 1. No, negative of half. And the examples are potassium superoxide, rubidium superoxide, cesium superoxide. This is the only superoxide that exists. That is what we come across in S block. But take the idea, everybody. So this is the varieties of oxidation state possessed by oxygen. Varieties of oxidation states by oxygen. Hopefully this is clear to all of you. Right. Then after oxygen, like there's so many types of oxygen and its oxidation state, we have another example called as hydrogen. So hydrogen can give you three type of oxidation state. Number one is elemental state. You all know elemental state is H2. So their oxidation state will be what? 0. This is having oxidation state of 0. Number 2, we have connected to hydrogen connected to metal or electropositive, more electropositive element. It is connected to metal or more electropositive element. Then the oxidation state comes up as negative of 1, like lithium hydride, sodium hydride, calcium hydride, etc. Then third, connected to a non-metal or more electronegative element. Then it is supposed to have oxidation state of +1. So the example could be water, ammonia, methane. If anywhere more electronegative element is there, then hydrogen, the hydrogen will be having +1 oxidation state, else it will be having a -1 with metal, 0 with hydrogen. Okay, so write it down and allow me a moment. I'll come back with my water bottle. Yeah, guys. So I'm back. Yeah, hello. Hi, Sumit. Hello, Shivanshi. Ram Ram, sir. Ram Ram to you. So, guys, that is hydrogen for all of us. Hydrogen has this much number of variable oxidation state it can show in its combined form. Now we'll come to the next element. We have halogen. So I'll also give you a few examples that if talk about fluorine. So the fluorine can exist to two state. One of the elemental state F2 where oxidation state will be 0. The another one could be F minus only. Fluoride. Example is HF. Fluoride is F minus. So their oxidation state will be what? Negative of 1. But that is what doesn't work with all the halogens. Other halogens can give you even more number of possible oxidation state. Let's take example of Cl, Br or I. One of them is X2. So there will be having 0 oxidation state because dihalogen is having two similar kind of halogen atoms attached with each other with a covalent bond. Another one is called as HX, that is hydrohalic acid. This will be having an oxidation state of -1. Then we have HX or HOX, hypohalous acid. This will be having an oxidation state of +1. HOX2 oxidation state is +3. HOX3 and HOX4. 3 has an oxidation state of +5 and this has an oxidation state of +7. This goes per halic acid, like per chloric acid, per iodic acid, per bromic acid, like that. Take an idea, write down every single part, very important part we have. So fluorine being most electronegative element of whole complete modern periodic table that will come across in our periodic classification of element chapter, but till then just take an idea that fluorine is the most electronegative element. So it has the tendency to basically attract the shared pair of electron to whoever the element is connected with towards itself is called as its electronegativity, and that is the maximum capacity of this element. So there we had the idea about all the different type of halogens and their possible variable oxidation state. Now I'll give you the idea like all the elements of group 1. So group 1 is like hey Leena, this is your lithium, sodium, potassium, rubidium, cesium and francium. All of them have an oxidation state of +1 in their combined state. Combined state as in whenever they are connected with some element, oxidation is 1. Group 2, we talk about group 2. What are group 2 elements? We have beryllium, then magnesium, calcium, strontium, barium, radium. These all have an oxidation state of +2, where in their undoubtedly their combined state. In its combined state it has this kind of. Now take you to group number 3. We have group number 3, no, it's group 13 actually. So boron, aluminium, gallium, indium, thallium, NH. So now it starts varying with its oxidation state because till aluminium to these are typically electropositive element and they have +3 oxidation state in their combined state whenever combined with any element. But talking about boron, boron can have BH3 in where boron has a -3 oxidation state. It can also apply to BCl3 where it has a +3 oxidation state. So +3 and -3 are two oxidation states that can be accepted by boron. Believe me guys, this is the most easy chapter. So if you follow my notes typically, and if you complete your lecture, if this lecture let's say takes 3 hour, 4 hour or 5 hour in one shot in complete theory coverage, if you stay there and if you maintain yourself being there, try and note down the whole notes with me, download the notes, link is given in the description, join our Telegram channel, then you can be assured that this was not so difficult chapter, sir. You explained it well and now it has become quite an easy chapter. So that is what oxidation states are all about. And I'll take you similarly guys, if you go to the group number 14, usually they have 4 and some variable depending upon what compound or combined state they are into, like carbon monoxide CO, carbon has positive 2 oxidation state, CO2 carbon dioxide, carbon has positive 4 oxidation state. Then it starts with variations, but group 1 and group 2 are said to have fixed oxidation state of positive 1 and 2 respectively, and group 13 can have positive 3, but boron can have -3 as well. So that's what we have to look into. Now we have another important rule here, that the sum of all the oxidation states. So guys, let us say there we are having one example. We have sulfate ion with us, SO4 2 minus, and there is one more example, we have H2SO4 with us, just 2. So guys, this is a neutral molecule, which we can see neutral molecule, and their oxidation state, hydrogen has a positive 1 oxidation state, sulfur over here has a positive 6 oxidation state, oxygen has a -2 oxidation state. Now you will say that sum of all the oxidation state will become 0 because the net charge is 0. So how do you say that? Sum of all oxidation states, 2 times of positive 1, 1 time of positive 6, that is of sulfur, and 4 times of negative of 2. This is 8 minus 8, answer comes up as 0. Can you see it? Let me explain one more example using sulfate ion. In sulfate ion, sulfur has an oxidation state of positive 6, this has an oxidation state of -2. Now do the sum of all oxidation state. How much does it come? 1 positive 6 plus 4 times of -2 is equals to -2. So -2 is equals to -2. So that's what we get. This is the net charge, -2. So what you will see, that if you know the oxidation state of all the remaining element and there is one element that you do not know how to find out, then using this formula of summation of the whole number of oxidation states of all the elements present inside it, whether it's an ion or it's a molecule, will be equals to the charge possessed by that molecule or ion. For molecule it will always be 0, for ion it is the net charge present over it. Now I can give you one more example from here. So let us say KMnO4 is one example we are taking. KMnO4, potassium permanganate is the name of this compound, and this has been underlined with Mn. So we have to find out the oxidation state of manganese. Potassium, we are very much familiar that sum of oxidation state of all will be 0 because the all molecule has a 0 oxidation state. So this is having positive 1 plus x minus, or like 4 times of -2, and this should be equals to what? 0, and x comes up as 8 minus 1 is equals to positive 7 oxidation state. I hope now you people are equally comfortable finding oxidation states of all the given one. Okay, let us see one more example. K2Cr2O7, potassium dichromate. In this compound we got to find out the oxidation state of chromium. How? So 2 times of positive 1, 2 times of x. So we always find out the oxidation state of one atom, not for whole the number of element or all the number of atoms present in one molecule. So we find it for 1 Cr, not for 2 Cr. 7 times of -2 is equals to 0. X comes up as 14 minus 2 divided by 2, that is positive 6. So that's how we can calculate easily oxidation state of whichever element we want to. Now, fractional oxidation number. What is the meaning of fractional? So actually this happens whenever we find out the average of some oxidation states. So let's take one example here. This is oxidation number versus oxidation state. Oxidation number versus oxidation state. Take this example, everybody. H2S2O3. There is a molecule called as H2O2O3, dithionic acid. And in this thionic acid, we have to find out, first of all, let us write the structure. This is the exact structure of this molecule. So using the structure, you can find out oxidation state of sulfur. See, this sulfur is pretty much isolated, oxidation state is 0, and this sulfur will be having, see, -1 from here, so +1, -1, same +1, -1, यहाँ पे +2 and -2. So let us say that this is your sulfur. I must write this is sulfur number 1 and this is sulfur number 2. So we can say that oxidation state of sulfur 1 is equals to 0. Oxidation state of sulfur 2 is equals to 1 plus 1 plus 4, positive. 1 plus 1 plus 2 is positive 4. So average oxidation state of sulfur, which is also called as the oxidation number of sulfur, will become what? 4 plus 0 by 2, that is positive 2. That's how we do. This is a difference, right? So in the similar way, we also have some example like carbon suboxide. Carbon suboxide. Formula C2O3. C2O3. No, C2O3, no C3. C3O2. C3O2, and let me check the C3O2 is correct. So guys, C3O2 has a structure like this. Like that. What is it, by the way? So 4 by 3. Let me check here. क्या है ये? C3O2 carbon suboxide. Got it. So the structure is like this: oxygen, double bond carbon, like that. So anyways, now we'll come back to the original thing which we are looking for. Oxidation state from here will be -2. If you break down this bond, it is positive 2. It is like 0. On breaking this, it will be like positive 2, and this is -2. So what we can say here, that average oxidation state of carbon will be how much? So average oxidation state is actually the oxidation number of carbon in this molecule or this compound will be how much? Positive 2 plus 0 plus 2 divided by 3, positive 4 by 3. This is equals to positive 4 by 3. I hope this is clear to all of you. So that is how we get the fractional oxidation states in some of the compound. So guys, this is one more thing we have. One question I would like to give you, and then I want people to understand. Okay, this is not positive. This is CrO5. We have a molecule named as CrO5, and we have to find out the oxidation state. So we have CrO5. Let us say if we apply our method, that x plus 5 times of minus 2 is equals to 0, x comes up as positive 10. But guys, if you look for chromium, whose atomic number is 24 and its atomic electronic configuration is argon 4s1 3d5. So like how many valence electron can you see? The number of valence electrons are 6. So the maximum electron it can lose is positive 6, and over here we find the oxidation state is coming as positive 10. How come is it supposed to lose 10 electron? So maximum possible oxidation state is how much? Positive 6, which you can lose all the electrons present in its valence shell. So now how can we justify its oxidation state 10? So guys, in such condition, there is definitely some of the elements of oxygen are not present in this form, oxide form. The structure there gives you the correct answer. Anyways, without structure also you can find out the value of oxidation state using one of my technique. First of all, you must know this is how this CrO5 structure look like, a butterfly structure. Now try breaking the bonds. This will be broken down, 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 this will be broken down. 1 2 3 4 5 6, positive 6. So the correct answer should be positive 6. So this is absolutely clear to all of you. Positive 6 is the correct answer. So guys, rest you can find directly by applying your concept anywhere, but there's you found some of the problem. So let us take this example. Let's say if over here we have three different ions. One is phosphate PO4 3 minus, another one is sulfate, and the one is dichromate Cr2O7 2 minus. So out of these three, if I have to find out the oxidation state of chromium, sulfur and phosphorus, what should I do? I'll simply go for the calculation that x plus 4 times of minus 2 is equals to minus 3. So x comes up as positive 5. Here x plus 4 times of minus 2 is equals to minus 2, and x comes up as positive 6. Here 2x plus 7 times of minus 2 is equals to minus 2. Then x comes up as positive 6. So what is the correct answer? What is the correct answer? 5, 6 and 6. 5, 6 and 6. Where can you find 5, 6 and 6? Okay, D is the correct answer. D is the correct answer. So that's how we find out the oxidation states usually. But in the cases where oxygen is not present in terms of oxide, or it is present in what we say fractional, then you have to apply some method. Not fractional, sorry. If it is present in peroxide or in like superoxide, then you have to find out. So superoxide had very limited number of example which I gave you, KO2, RbO2, CSO2 before, and right after that we will be understanding some peroxide examples. Take this question: in which of the following compound oxidation state of iodine is fractional? So guys, IF7, iodine will be having a positive 7 oxidation state, positive 5 over here. IF3 positive 3, but over here we have 3x is equals to minus 1, so the oxidation state comes up as minus 1 by 3, which is fractional. Correct answer should be B. Hopefully this is absolutely clear to all of you. So We have one more example here. H4 just simply apply our concept that since it is connected to a electronegative element, phosphorus and hydrogen is supposed to have a bit more electropositive than phosphorus, so we'll say hydrogen is acquiring positive 1 charge, and also oxygen is directly connected to hydrogen somewhere, so we can simply say that hydrogen will be acquiring a positive 1 charge. 2 times of x, 7 times of minus 2. This is equals to 0. So x comes up as 14 minus 4 by 2, that is positive 5. Oxidation state is positive 5. Solving the another one, we have 4 times of plus 1, 2 times of x plus 5 times of minus 2 is equals to 0. Next comes up as 10 minus 4. So 14, and this will be 10 minus 4 by 2. This is 10 minus 4 by 2, which is 6 by 2. Positive 3 is the correct answer here. And the last, 4 plus 2x minus 12 is equals to 0. X is 12 minus 4 upon 2 is 8 by 2, that is equals to positive 4. Correct answer 5, 3 and 4. Where you can find 5, 3 and 4? D. This question came in JEE Main 2021. So not a problem when we'll be doing our practice exercise, where from 2002 to 2024 all the questions appeared in JEE will be explained here. There we'll cover the practice part and all the PYQs. Until then, keep your content and your theoretical knowledge with you. Then we'll apply and get questions. Okay, that's how we do it. So I guess that is the enough of number of the questions we had. Now I must give you the idea of where can you find out the peroxy bond and like that. So guys, I have a very amazing trick for all of you. So we have number one case, the case 1, where the calculated oxidation state comes lesser than maximum possible oxidation state. In that way, guys, you will definitely be having there is a CM bond. What is CM here? Let us say CA bond. CA bond, that is central atom. Right? You might not be getting this example now, but using one example you can find out. Example is H2S2O3. So the dithionic acid I was talking to you about, H2S2O3 is one example, and sulfur is the element that we have to find out its oxidations for. We all know sulfur has a maximum possible oxidation state of positive 6, and calculated oxidation state will be how much? Tell me. So this will be 2 plus 2x minus 6 is equals to 0, and x comes up as positive 4 by 2, so this is positive 2. So this belongs to the same example. So in this example, wherever this is given to us, there is definitely CCA bond, and in this way the oxidation state of central atom will come up as same as calculated. same as calculated. So whatever you calculated right now, that is the correct answer. And you can even see positive 2 is the correct answer. The correct answer is positive 2. So the answer over here is plus 2. You can find out one metal-metal bond also using its structure, its complete structure. How does this structure look like? See, this is how the structure look like. So can you see a metal-metal bond here? Because I can. Metal-metal bond. Another such example could be H2S2O5 or no, it's fine then. Okay. These are the so there is a central atom. All oxygen are oxides. All oxygen are oxides. Number 2, case number 2. Case number 2 we have, if maximum oxidation state is equals to calculated oxidation state, then calculated then oxidation state calculated or maximum possible will be the correct answer. And there's a possibility there will be there's a central atom oxygen central atom bond is there, and this is actually called as oxy bond. Oxy bond. Now I'll give you one example and then you'll understand what we are talking about. Example is H2S2 H2S2O7 oleum. H2S2O7 molecule is called as oleum. So the structure of oleum looks like this. S double bond O, one O is there. Haven't you seen what I was talking about? So I was talking about this bond, this metal and oxy bond. So oxy bond is there, and what is the oxidation state? That is 2x plus 2 minus 14 is equals to 0. X comes up as positive 6, and this is also equals to its maximum possible oxidation state. So that is your case number 2. Always take in your mind this is your case number 2 in finding the oxidation states, and if you stuck in such way where maximum possible oxidation state and your calculated oxidation state are coming the same, and the maximum you can take an idea using its electronic configuration. Next is case number 3. Case 3 is somewhere where oxidation state calculated is lesser or is greater than oxidation state maximum possible. If it is coming even more than the maximum possible oxidation state, then definitely there is a problem. What is the problem? Then there is definitely metal bond is there, bond, or simply OO bond is there. This is called as peroxy bond. So guys, in these way, normally the correct oxidation state or the correct answer will be is the maximum possible oxidation state. Oxidation state maximum possible. So that's we can find out. Let us take one example. Example is H2SO5 called as peroxysulfuric acid, also called as Marshall's acid. No Marshall's acid, it is called as, I forgot the name, Keros acid. So Keros acid has its structure like S double bond OOH, then OH double bond O and double bond O. So guys, if you want to find out its oxidation state maximum possible, that is positive 6. If its oxidation state you find out calculated, it will come up as 2 plus 10 minus x equals to plus x equals 0, x comes up as positive 8. So you know that positive 6 is the correct answer. So the correct oxidation will be positive 6. And this is the bond we were talking about. This is actually the bond, peroxy bond, that we were actually talking about. This is your definitely peroxy bond. All set, all right, all well. Let me take you one more similar kind of example. So take this example. H2O8, and it is called as Marshall's acid. Marshall's acid, or there is one more name we use for this acid called as peroxydisulfuric acid. So its structure somehow look like this. So guys, we have two oxygen atoms as peroxide here. So this is called as your peroxy bond. So you cannot take all the oxygen as -2. So that is why your calculated oxidation state will come up as greater than the maximum possible one. This is your peroxide bond. And in the peroxy bond, both of the oxygen atoms are peroxides with -1 charge respectively, not with -2. And in calculation, or while going for the calculation of oxidation state, you took all the oxygen as -2, and that's where we committed the mistake. So our mistake will be corrected by this. So yes, wow. So the correct oxidation state will be, so if you calculate the oxidation state, then how much will it come? Oxidation state calculated, see, 2 plus 2x minus 16 is equals to 0. X is positive 7, which is even more than the maximum possible, because oxidation state maximum possible is how much? Positive 6. So now you compare them. So the correct answer should be what? The maximum possible itself. Like that. So very good everybody. Now let us move forward. We have now the next part of this chapter, oxidizing agent versus reducing agent. So do you know what the meaning of an agent is? For an example, if I have a flight agent and he books flights for me, so whenever he books a flight, it's me who have to fly away, it's me who have to travel, not him. So an agent does something and itself gets opposite of that. It itself gets opposite of that. For an example, in oxidation and reduction, somebody has to do reduction, that is why another will go oxidation. So oxidizing agent is something, agent that will oxidize the front person or the front chemical species, not self one. So itself will be getting reduced if it is an oxidizing agent. Similarly, if it's a reducing agent, it will reduce the front species, it will self automatically will get oxidized. So that's what an oxidizing and reducing agent mean. So before going for further detail, let me give you a quick example. Everybody, we have K2Cr2O7. We do not have any balanced chemical reaction, but we'll know how to balance this reaction right after this part and very shortly. Initially we have one chemical reaction, Fe2 plus, and this reaction happens in acidic conditions. And this is happening in H plus conditions. Products are CrSO4 plus Fe3 plus. Now try out everybody who is oxidizing agent, reducing agent, everything I'll tell you. First of all, you just assign them their oxidation states respectively and do not assign each and every element oxidation state. Just identify which may go change in oxidation state. Apply your oxidation state to those elements only. Over here we have seen oxygen is present in oxide only. No need to assign. Chromium, it always presents in positive one. We not need to assign. Positive 6 oxidation state is there for one chromium atom. From there it is going to positive 2 oxidation state. How? Because the sulfate ion has a -2 charge. Chromium will definitely be having a positive 2 charge, like that. Very good. Then we have one more species which is having positive 2 charge and going to positive 3 charge. So no doubt this species is undergoing oxidation. This process is what? Oxidation. And oxidation is happening of what? Oxidation is happening of this Fe2 plus. So Fe2 plus has become what? Reducing agent. How come it is a reducing agent? Because it is reducing the front species and itself getting oxidized. Now the similar way we'll take another one. We had chromium from positive 6 oxidation state to going to positive 2 oxidation state. From 6 to 2 something is going in decreasing oxidation state is called as reduction. So in this reduction it will become what? An oxidizing agent, because something which is undergoing reduction will become itself as an oxidizing agent. That's what oxidizing and reducing agents are. That's the simplest concept of oxidizing and reducing agent in front of you, everybody. So just try writing it and try to apply the concept. Chaliye. Then we'll come to some of the questions from here. One example is here given, H2S. Now you all should be very much comfortable in finding the oxidation state. There are like plenty of examples you can find. Whatever the molecule you see, just try to find out the oxidation states in each and every one out of them. And even I can give you some example. So even as a homework I can give you. So HCl, HNO3, H2CO3, H2C2O4, HCl, O, HClO2, HClO3, HClO4, H2SO3, H2SO4, H2S, H2S2O3 H2S2 O7 So guys, I'm underlining those elements for which you have to find out the oxidation states: nitrogen, chlorine, carbon, carbon, chlorine, chlorine. For central atom, you got to find it out. Okay, chlorine, chlorine, sulfur, 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 sulfur. Then sulfur, 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 manganese, chromium, iron, copper, cobalt. So for these all you have to find it out. Okay, this can be given in terms of ions also. So somewhere you can get these in terms of ions also. Ions as in let's say carbonate ion, sulfite ion, sulfate ion, bisulfate ion, permanganate ion, dichromate ion. Right, perchlorate ion, chlorate ion, and then chlorous ion, hypochlorous ion. This is something you do. So I'm underlining the element that you have to find out the oxidation state for: sulfur, sulfur, manganese, chromium, chlorine, 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 phosphorus, 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 sulfur, and sulfur. So guys, you have to find out the oxidation states of these as a homework, and believe me, right after doing this, it will give you a lot of huge confidence to solve the problems and to understand this chapter. I'm also explaining one example over here. Let us suppose cobalt, Cl2. So in this example, these kind of compounds are called as complex compound, which we usually don't study in 11th standard, but yes, it will be very much useful in coordination compounds chapter, which will be appearing in 12th standard. Very soon you will find these kind of questions or concepts and compounds also. So here we have to find out with cobalt. So assume it as X plus. Chlorine is always present in form of chloride, which is directly bonded to CO, cobalt. So -1 plus. Ethylene diamine doesn't have any charge. This is like ammonia. NH3 has no charge. NH2, CH2, CH2, NH2, and it's a species complete which can donate two lone pairs from two nitrogen atom but doesn't have any charge over it. So I'm giving you an idea. Then there is one more chlorine atom. For -1 you can apply, is equals to 0. X will be coming up as +3. So this is present in +3 oxidation state. So this is how you can solve the example. I gave you for one or two or couple of more examples there. One in terms of iron also is there. Now oxidizing agent, reducing agent is completed here. Okay, there was one more example we were explaining. For H2S we have -2 oxidation state. You just solve everything 4 I have given to you, and then you will come to this conclusion that you know oxidation states of all the element given in a particular reaction, just like me. So I know iron is over here is in positive 3 oxidation state, iron has reached to positive 2 oxidation state, sulfur has reached to 0 oxidation state, rest are in the same oxidation state, and I don't need to mention them. Like talking about hydrogen is in +1, everywhere it is in +1, there is no change, we don't need to mention it, and unnecessarily it will basically confuse us. From -2 to +2, something is going from minus to positive, it is oxidation, but it's wrong, it is going to 0, although it is an oxidation process. So this will become what? Something from +3 going to +2 is no doubt reduction process. So whoever is undergoing reduction will become an oxidizing agent, and something which is getting oxidation will become reducing agent. This is how we find out the agent. We call as oxidizing agent as oxidant, we call reducing agent as reductant, based upon their names only. So there is one more concept I want to give you, that something which is already present in maximum oxidation state, something which is present in its maximum oxidation state, it can only undergo reduction. It can only undergo reduction, that's why it will always work as an oxidizing agent. Can only undergo reduction. Why? Because it is already having maximum oxidation state. We cannot increase its oxidation state. What we can do is decrease its oxidation state, and decrease in oxidation state is called as reduction. Then if we are having if oxidation state is equals to minimum oxidation state, if we have minimum oxidation state, then it can only increase its oxidation state. So it can only undergo oxidation because it is present in minimum, and something which is going oxidation will always be a reducing agent. And similarly, the one which is present in between of everything, in between as in if it's an oxidizing agent, or like its oxidation state is between minimum and maximum. So let us take one example here. This is called as hydrogen peroxide, H2O2. And in hydrogen peroxide, you can find out the oxidation state of oxygen using the same formula which we were earlier doing. 2 plus 2x equals to 0, 2 is equals to minus, 2x equals to -2, x equals to -1. Now this -1 can go to either of the oxidation state from here. Let us suppose this is undergoing a process called as oxidation. In oxidation, oxygen will be leading you to formation of O2, and O2 has an oxidation state of 0, -1 to 0. So here H2O2 is working as what? H2O2 is working as reducing agent. Similarly, if I take it to H2O where the oxidation state of oxygen is -2, in this way this process is reduction, and in reduction H2O2 is working as oxidizing agent. Please understand it, please read out it, and then you will become highly confident on the ongoing topic. Please do it. Right, guys? Let us have some few questions. Some of the questions are here. Question says that hot concentrated sulfuric acid is moderately strong oxidizing agent because sulfuric acid has sulfur in +6 oxidation state, and wherever oxidation state of sulfur decreases, because it cannot be increased, it's the maximum oxidation state, wherever it decreases, oxidation like H2SO4 will work as a oxidizing agent wherever its oxidation number decreases. So here we can see that sulfur is in +6 oxidation state and some sulfur is in +4 oxidation state. So something which is going from +6 to +4, definitely it's a reduction, and something undergoing reduction, this will be called as an oxidizing agent, and this process from +6 to +4 is reduction. So something undergoing reduction is the oxidizing agent, opposite. Same here we can find out. Same here. Sulfur over here is positive 6. Positive 6 to it is going to positive 4. Another similar example. Similarly, positive 6, we have positive 4. But here, positive 6 is here. And also over here, positive 6. Since it is positive 6, positive on both sides, H2SO4 is not working as a reducing agent. It's not even working as any agent. Its oxidation state is the same. It's not even undergoing redox reaction. That's how we find it. Correct answer D. Next topic is types of redox reactions. How many types of redox reactions are there? So very first of them is called as combination reaction. One is called as what? Combination reaction means addition reaction. Decomposition, displacement, disproportionation. So we have plenty of reactions here. Let us start with very first, called as combination. Name itself suggests that whenever two species are added giving one single output, then such kind of reactions are called as combination reaction. But there is a condition that at least one of the species which we are adding must be present in its elemental form. Must be present in its elemental form. So where is it written? Anyways, see, either of the A or B which are combining must be present in its elemental form. So for this I will give you one example and then you will come up with such a good conclusion. Example. We have CaO plus CO2 producing CuCO3. In this reaction, I'm asking you whether this reaction is an addition reaction or not. You will say yes, because two species are added giving one single species. I'm asking you whether the given reaction is a redox reaction or not. The answer will be no. Why? Because calcium in positive 2 and carbon is positive 4 and oxygen in minus 2. It is going to calcium in positive 2, carbon in positive 4, oxygen in minus 2. None of the oxidation state is changed. So that is why it was said that whenever you find out an addition reaction as a redox reaction, there must be one of the reactant present in its native state or in reference state or in elemental state, uncombined state it must be there. So that is what we found it over there. Right? Everybody? Maybe we can take one more example to explain the same part. C plus O2 producing CO2. What we find is both of them, let it be oxygen, let it be carbon, both of them are in reference state, or we can say elementary state. So if they are in elementary state, let us write their oxidation state. This is oxidation state is 0 in its native state. This is 0 and this is going in positive 4, this is going in minus 2. So we can find the change in oxidation state from 0 to minus 2. 0 to plus 4 will give you what? Oxidation, and 0 to minus 2 is reduction. Since oxidation and reduction both are happening simultaneously, this reaction becomes a redox reaction. So can I call this reaction as an addition reaction? Yes, it is an addition reaction. Is this reaction a redox reaction? The correct answer is yes. That's how we do it. Then comes decomposition reaction, but always make sure one of the product. So initially what we are saying in addition reaction, that one of the reactant must be present in its elementary state, native state. Similarly, in decomposition reaction, one of the product must present in its elementary state. So from H2O, if we are electrolyzing it and producing H2 and O2, this is how the products are produced. And similarly from here, okay. So guys, I have one more perfect example for you. KClO3 on heating gets down into KCl plus 3/2 O2. Now my question is, this is solid and this is solid and this is gas. The question is pretty simple to all of you. Is it a decomposition reaction? Because yes, one of the substance is undergoing into decomposing and producing more than one substance. So this is yes, but is it a redox reaction? Can we call this reaction as decomposition redox reaction? Then the correct answer should be yes, sir. Why? Because sir, one of these species must be present in its elementary form. So now you can even check it applying or assigning the oxidation states. K has positive 1, no need to write. Cl has positive 5 oxidation state, you can find out. Potassium chlorate. Oxygen has oxidation state of -2. Chlorine has an oxidation state of -1. Oxygen has a state of 0. So chlorine positive 5 to -1 is undergoing what? Reduction. And oxygen -2 to 0 is undergoing what? Oxidation. And this type of reactions are called as intramolecular redox reaction, in which out of one molecule only one of the species is undergoing oxidation, other is going reduction. So guys, third reaction is called as displacement reaction, and all the displacement reactions, and let me write it, that all displacement, no, I'll write it in the next page then. So displacement, one of them is displacing another element, and it could be two types of reaction. One of them is called as metal displacement reaction. One is called as metal displacement reaction. Now check it out. We have a metal, zinc, on reaction with copper sulfate, reduces it to copper and itself produces zinc sulfate. So guys, can you identify their oxidation states and their changes? Yeah, we can. Zinc 0, copper positive 2, copper 0, zinc positive 2. Now you can identify reduction and oxidation. Most importantly, what you find is zinc has displaced copper of less reactivity out of it. This is called as metal displacement reaction. And another example could be non-metal displacement reaction. So what happens in non-metal displacement reaction? Let us take this example. We have a non-metal H2O reaction with fluorine produces HF plus oxygen. So in this reaction, what we understand is the oxidation number of H2O. Oxygen is -2, fluorine is 0, -1, and then 0. So there we can find out that fluorine being more electronegative and more reactive displaces oxygen as a non-metal out of H2O, forms HF as a product, and oxygen is eliminated out. So that is what we can see. Oxygen is undergoing reduction. I think this is it. I think no oxidation is undergoing oxidation here. So this is your called as displacement reaction. So I would like to add one point here. I want to add one point here. Write down it as a note that all displacement reactions are whatever it is there, are redox in nature. All the displacement reactions are redox in nature. Whatever the displacement reaction is you have been given up with. Example, displacement reaction. So let us say we are reducing iron with carbon, producing iron and CO2. The reaction happens in blast furnace in production of iron. So there you can see that all of them are redox in nature. How? Carbon from 0 has reached to positive 4. That means carbon is undergoing oxidation. But on the other end, we have positive 3 oxidation state which is going to 0. So this process is actually reduction. And the overall reaction is redox. We have one more note to write down, note number 2, that says that all double displacement reactions are non-redox. They are non-redox in nature. All the double displacement reactions are non-redox reactions. How? Let us take one example. So the example could be Na2SO4 plus BaCl2 gives BaSO4 plus NaCl. So guys, can you find out the oxidation states here? We all know how to find it out. Sodium has +1, sulfur has +6, oxygen has -2, barium has +2, chlorine has -1, barium has +2, sulfur has +6, oxygen has -2, sulfur, sodium 1, chlorine -1. Does any one of the element is undergoing change in its oxidation state? Is anyone is like undergoing the change in oxidation state? None. That is why this is called as non-redox reaction. Note it down. So now we'll come to the next reaction called as disproportionation reaction. So disproportionation reaction is pretty simple, everybody. It's just difficult to take the name. And I remember my days of when I initially joined this organization or this field of teaching, and I was like under a coaching program, a training program where teachers were trained to give the lectures. And in that training program, my reporting faculty, the reporting manager, gave me a task to teach this reaction as a topic, and this reaction was disproportionation reaction. By that time, I tried explaining it disproportionation. Every time I used to do this I was not pretty much able to speak this name, and I thought by that time that now I should do one thing, that I keep on revising this term in my mind, and the moment my lecture comes, I'll shout with the name disproportionation reaction at once, not for every time, and rest of the time I'm calling it DP reaction. And that's how I saved my life by that time. So disproportionation reactions, I used saying DP reactions. The lecture went well, everybody was amazed, and everybody had this appreciations of like that was a good topic you taught, sir, and clapping. Then immediately one of the head reporting manager asked me out of this class only, he was also sitting and giving me the marks, Sanjay sir, everything was brilliant. from where did you learn this DP reaction name? And I was like, DP reactions, sir, DP reaction, I made it by myself because it's difficult to pronounce disproportionation reaction. So they said, okay, like that was good. Like we have to tackle the situations in whatever the mode we are right now in, but we always have to fight with the existing problems. Now coming back to our topic, that is disproportionation reaction, and let me give you a perfect example, and let me give you an explanation behind it, that whenever in a particular reaction, simple one molecule or ion out of one molecule or ion, one element only, let it be phosphorus, zero oxidation state, undergoes oxidation and reduction. So here it has -3 oxidation state because of hydrogen is in +1, and here phosphorus has an oxidation state of +1. So something undergoing 0 to +1 is called as oxidation, and something going from 0 to -3 is called as reduction. So if same element that belongs to same molecule or ion undergoes oxidation and reduction as well, it's called as disproportionation reaction. Very simple reaction, right? A similar type of reaction is called as comproportionation, which is just the reverse of disproportionation reaction. Just the reverse of disproportionation reaction, called as comproportionation or symproportionation reaction. Thankfully, I was given the task to teach only disproportionation, not comproportionation. Otherwise, anyways, now coming, I would have made some more abbreviations. This is like CP reaction, and that would have become SP reactions, symproportionation. Guys, exactly opposite thing is happening. We have two different species in which two elements, the same element, but in two different species. Let us say this is like NH4 positive here, and this somewhere is NO2 negative here, and the oxidation state is pretty clear to all of us. This is +3 and this is -3. So -3 and +3, this is going to N2, which is 0. So something going from -3 to 0, it is oxidation, and something going from +2 to 0, it is reduction. So if reduction and oxidation are happening from two different species, element might be the same, two different species, and entering to the same oxidation state of that species or that element, then it becomes symproportionation or comproportionation, opposite to the disproportionation reaction. So there we end with this topic. Now we have some question for all of you. Let's see who can solve this question. The question is pretty simple. Says an example of a disproportionation reaction is, where can you find the example of a disproportionation? So we have to find out the oxidation state first, and then we'll see where we can find the change. So this is permanganetine. Permanganetine is +7 in oxidation state, and then this is +2, and this is positive. So this is only +2. So it's a simple, what we can find it. It's simple reaction in which only reduction is happening in manganese. So we do not find any disproportionation. This is copper in +1 oxidation state, copper in +2 oxidation state, copper in 0. If copper from copper bromide is going to oxidize as well as reduced from +1 to 0, it is also going reduction. If oxidation and reduction both are happening simultaneously, then this reaction becomes what? Disproportionation reaction. Next topic is balancing of redox reaction. So guys, we have two different processes of balancing of a redox reaction. One of them is called as using oxidation number method. So this is basically more important process, because this process is a faster process. But it requires a knowledge knowledge of equivalence concept, knowledge of equivalence concept and n factor. This requires a knowledge of n factor and equivalence concept. Now coming to the half reaction method is a more simpler method. It's a bit time taking process. It's a time taking process, but gives the correct answer every time. So anyways, this is the more preferred method. So this is the more preferred method, but initially we will initiate with half reaction method unless we are aware, about the equivalence concept. Unless we know about the valency factor or n factor or equivalence concept, we have to study the oxidation number method first. So I'll take you to oxidation number method. There are set of things that we have to follow while going to balancing something under oxidation half reaction method. There is one more thing I want to add is few of the points from oxidation number method or this method, half reaction method, are very common. So please engage yourself and be more focused right now, because upcoming 5 minutes are going to be highly important for all of us. Very first thing is just you need to identify where you are getting the oxidation reduction. How can we get it? Sir, iron is in positive to oxidation state. You are not supposed to assign the oxidation states on everything and whatever it is given up. Just simply take the idea. Okay, let's say in this reaction there is one more thing given. So let us say this is given in like H positive is given, and let's say somewhere we are given up with H2O, right? This is the reaction. So step 1 says, the step 1 simply says, write only those species in main equation undergoing oxidation and reduction, and do not write H plus, OH minus, H2O, salts, etc. Salts as in unnecessarily K2SO4 is given, N2SO4 is given, which is not even undergoing any change in oxidation state. We don't need to write it. So the first step says that according to first step, follow the first step and you simply write it in this way: Fe2 positive plus Cr2O7 2 minus, giving you Fe3 plus Cr3 plus. So that is the first step. We got it till here. That's we call it as first step. This is your first step. Clear? I think we all are clear up to first step. Then we reach to the second step. What is the second step? Step 2 says that assign oxidation number to those elements undergoing, what is happening here? Undergoing oxidation and reduction, and divide whole equation into two halves, which are these two halves. So first of all, let us take these two examples, Fe2 plus Cr2O7. So this was given to us, Fe2 plus Cr2O7 2 minus Fe3 plus Cr3 plus. Now bring on the oxidation states, everybody. Positive 2, positive 6, positive 3, positive 3. From positive 2 to positive 3, we find it as oxidation, and we from positive 6 to positive 3 find it as reduction. So now you split all into two equal halves. Number one is called as oxidation half reaction. How should we write an oxidation half reaction? This is your iron 2 plus goes to iron 3 plus by losing one electron. The change in the charge is only. This is called as oxidation half reaction. Next is reduction half reaction. So reduction half reaction is Cr2 O7 2 minus, except some number of electrons gets converted into Cr3 plus. First of all, you balance the number of chromium. Here 2, put a 2 number here, and 1 chromium from positive 60 going 1 chromium, guys, I'm taking this idea from here. This is going from positive 2 to positive 3. This is going from positive 6 to positive 3. So something is undergoing a change in positive 6 to positive 3. Something undergoes a change from positive 6 to positive 3 will acquire 3 electrons. One chromium atom from positive 6 to positive 3 acquires 3 electrons. So what about 2 chromium atoms? It will acquire 6 electrons. 6 electrons it will acquire. So that's how we are going it. But the balancing of rest of the elements such as oxygen, hydrogen will be done later on. The only thing that undergoes a change that has to be balanced at first in the half reaction itself. Now you multiply both of the equation by suitable numbers so that you can make electrons equal in both the way, lost equals to gain. So lost are how many? 1 multiplied by 6 and multiply here by just 1 and then add it. So I will write step number 3. The step 3 says that multiply both half equations by suitable number to make electron gain is equals to electrons lost. If the number of gained electron equal to the number of lost electron, then what we do is electron gain are right now equals to electron lost, and then add both half reactions. Add both half reactions. So both half reactions were this was like 6 times of Fe3 plus, not Fe2 plus, was going to 6 Fe3 plus plus 6 electron, and the another reaction was Cr2O7 2 minus plus 6 electron gets you into 2 Cr3 plus, and now you add them. So on adding, 6 electrons are cancelled out. It will become simply 6 Fe2 plus Cr2O7 2 minus gives you 6 Fe3 plus 2 Cr3 plus. This is what it has become now. This is your step number 3. Now comes step number 4. Step 4 says that balancing of oxygen. Balancing of what? Oxygen. How do you balance the oxygen? By adding an equal number of H positive, adding equal number of H2O molecules, because as many H number of oxygen are missing, add H2O molecules in the hydrogen deficient site. In oxygen deficient side. In oxygen deficient site. So the reaction becomes 6Fe2 plus Cr2O7 2 minus gives you 6Fe3 plus Cr2Cr3 plus. Now how many oxygen can you see in left hand side? 7. How many oxygen are here in right hand side? 0. So it will become 7H2, right? Then step 5. The final step is balancing of hydrogen. How to do the balancing of hydrogen? So there are two cases. Case 1, in acidic medium. So guys, what we do in acidic medium? Just simply add equal number of H plus ions in hydrogen deficient site. Equal number of H plus ions in hydrogen deficient site. How does it become? Now what does it become right after that? It was already 6Fe2 plus Cr2O7 2 minus, and it produces 6Fe2 plus 3 plus 2Cr3 plus 6H2O, no 7H2O. So we simply provide it plus 14H plus 14H positive. So believe me, right after adding this extra term of 14H plus, now this has become as a this is your balanced chemical equation. But what we are doing here, we are balancing it in acidic conditions, right? We also have to come to case number 2. Case 2 says that balancing of hydrogen in basic medium, where OH negative ions are given. So what you will do? This is a beautiful part. So balance the reaction up to hydrogen balancing in acidic condition, and add equal number of OH minus ions in both sides equal to hydrogen. So how many number of H positive you added? Just add equal number of OH minus ion in both of the sides of the reaction. LHS and RHS you have to add as many as number of OH minus ion. Then the reaction will become what? Let us see. 6Fe plus Cr2O7 2 minus 14H plus gives us 6Fe3 plus 2Cr3 plus 7H2O. So you are adding 14 OH minus here, and you're adding 14 OH minus here. So after adding 14 OH minus, you will see that this portion has become equals to 14 H2O. 14 H2O are here, 7 H2O are here. What will the final reaction, balance chemical equation? The final balance chemical equation will be 6 Fe2 plus Cr2O7 2 minus. This is 14 and there is 7. You will get 7 H2O remaining. 7 H2O gives us 6 Fe2 plus 2 Cr3 plus 14 OH minus ions here, because water has been eliminated out. This is a balanced chemical equation. Now this is your balanced chemical equation. That is what we do in acidic and basic condition. So guys, please revise it, write it properly, and try to understand how we are balancing in both acidic and basic medium. And all the processes will be similar. Let it be whatever the kind of process we are picking, let it be ion electron method or half reaction method, or let it be oxidation number method or n factor method. Some of the points will be same, that is balancing of oxygen and hydrogen. But until then, everything has to be done by our end. This is how we do it. This is what we do in basic condition. Now take one more example. In basic condition, we have to balance this reaction. So what we are going to do is, we are first assigning the charges. 0 oxidation state, positive 5 oxidation state in nitrate, positive 2 oxidation state in zinc, minus 3 oxidation state in ammonium, or that is it. So what you see, that zinc is undergoing from zinc to positive 2. So this is what? Now just you split them. Okay, zinc on losing 2 electron gives it in 2 plus and 2 electron, and this reaction is called as what? Oxidation half reaction. Then we have another reaction, nitrate ion. Nitrate ion on acquiring 5 or what? Okay, 8 electrons. 5 to minus 3 something is going, 8 electron has to be taken, and it is converting into NH4 positive. If you are confused, just use this data, that 0 is going to positive 2 by acquiring like losing 2 electron, and from positive 5 something has to go to minus 3, then 8 electrons need to be accepted. This has become what? Reduction half reaction. So what we can do is, we can simply add these two reactions by balancing the number of electrons. How? I told you, multiply this reaction by 4, multiply this reaction by 1. No, or oppositely I have done, multiplied by 1, and then get the final equation, and then we'll do the further treatment right after that. So this is 4 zinc, 4 zinc plus 1 nitrate undergo following, giving you 4 Zn2 plus simply NH4 ion. So we have got something which is balanced in terms of number of electron gained equals to lost. This is where we are getting the main equation. So now we'll do the oxygen balancing. We all know how to oxygen balancing. How is oxygen balancing done? 4 zinc plus nitrate ion producing 4 Zn2 plus and plus 1 ammonium ion. So there are 3 and there are 0. So we will add 3 H2O in right hand side. After adding 3 hydrogen nitrate side, balancing of Oxygen has been done. Oxygen, let's see, I'm doing it by balancing of hydrogen is to be done. 6 are here, 6 plus 4, 10, and here we are having 0, so we'll add 10H plus. And not just 10H plus, it is conducted in basic medium, so 10 OH minus are also added here, and 10 OH minus are also added here. So after adding, this will become our final equation, that 4 zinc plus 1 nitrate ion. Then this is 10 H2O, and right hand side there are 3, so it will be having 7 H2O. So produces 4 Zn2 plus 1 ammonium NH4 plus ion plus 10 OH minus ions. This is your balanced chemical equation. Correct, everybody? Now you want me to give you a best trick to identify the Brahmastra, to identify whether our given reaction is correct or not. So how to check whether given reaction is balanced or not, is balanced properly, balanced correctly. So there is a trick that just do one thing. The sum of all charges, no doubt elements so will be balanced only, but sum of all charges left hand side must be equals to right hand side. If you know that left hand side and right hand side charges are balanced, then the reaction will be chemically balanced. Now take both of the examples, everybody. The one example that we did a few slides before, this reaction, that 6Fe2 plus 14H plus 6Fe2 plus Cr7 2 minus plus 14H plus gives you 6Fe3 plus 2Cr3 plus 7H2. So guys, this is the balanced chemical equation we did. Now take LHS must be equals to RHS, total charge. So how much is LHS? 6 into positive 2 plus 1 into minus 2 plus 14 into positive 1 must be equals to what? RHS 6 into plus 3 plus 2 into plus 3. So this has become what? 12 plus 18. I think this will come up as 18, and this will also be coming at somewhere like that. So 12 plus 14 minus 2 is coming as 14. Is it not balanced or what here? It's balanced 24 both sides, no? Yes, 24 only. Correct. Okay. So this is positive 18, both of side, which is coming up as positive 18. Positive 18 is equals to positive 24 equals to positive 24. So that's how we do it. That is the trick that we use. So guys, until then, let me just remind you, we right now are having 2 special features on our Unacademy app, for which you can get the link directly in our description part. Go there, and this is All India Mock Test IIT JEE 2025. So just use it. The next test is going to happen on 12th of January. It will give you exactly the same simulation that you are going to find in your main exam. So that will give you an idea. Best quality questions will be there. Along with that 2025 exam JEE Main, the first attempt you are preparing for the demo paper. You will be also having one rank predictor with you that can help you to identify where do you stand right now, what marks are you getting, what has to be implemented from here. So please go to the link given in the description part. And then we have the next concept, equivalence concept. But before starting equivalence concept, let us take a small break. I'm feeling a bit hungry. You also have some evening snack, and we'll join back in just 15 minutes from here. Okay. Hello. So guys, am I live? Yes, hopefully I am. Uh, Very nice. So till now we have covered the first part of this chapter, that is balancing of redox reactions using ion electron method or half reaction method. And now we'll come to the next part called as equivalence concept. So guys, let me give you an idea. How can we relate the equivalence concept with mole concept? Okay. Mole is a parameter or a quantity. Using that, we can quantify some given substance. In the similar way, equivalence is also that quantity. Using that, we can quantify a particular substance. But there is a different type of relation between moles and the number of gram equivalents. So first of all, let me give you an idea. Like, first, let me say some reaction is given to me. Some general reaction is here. We all know Haber's process of preparation of ammonia. So N2 plus 3H2. N2 plus 3H2 gives us 2NH3 in this reaction called as Haber's process. Nitrogen and hydrogen are combined together to give you ammonia. So what we have to do is, let us suppose we have been given here with number of moles. If we ask about, so if we talk about number of moles, so these number of moles required to react, let's say, is 1. 1 mole of nitrogen requires 3 moles of hydrogen to react with and will produce 2 moles of ammonia. That is what we have covered in mole concept. This is called as mole concept. And mole concept requires the balancing of chemical reactions. Then we have number of gram equivalents, another important parameter called as number of gram equivalents, EQ. Gram equivalents. So this has a gram equivalent of 6. It has a gram equivalent of 6, and this also has a gram equivalent of 6. Now this is very amazing part, that if we observe this number, we found that number of gram equivalents are equal. Number of gram equivalents are usually equal, 6, 6, 6 and 6. Similarly, everybody, if you observe this number, you will also find that when 1 was multiplied by 6, it came 6. When 3 was multiplied by 2, we got 6. And when 2 was multiplied by 3, we got 6. So what are these 6, 2 and 3? These 6, 2 and 3. So first of all, this 6, 6, 6, what we have got here is actually the equivalence concept or equivalent concept. Equivalent concept. This is mole concept, this is equivalent concept. So equivalent concept says that gram equivalents of all the reacting and product species will be equal. And what are these 3 numbers? These 3 numbers are called as the N factors or valency factors. So there are 3 different quantities we got. One of them is called as number of moles. When number of moles of something is multiplied by its N factor or valency factor, it gives you another quantity. We call it equivalents, so gram equivalents. How to determine this N factor? How can we convert moles and everything into each other? Let us discuss everything one by one by taking the definition of 1 gram equivalent. What is the meaning of 1 gram equivalent? So if we talk about in the terms of acid or base, an acid that can give you 1 mole of H positive ions is called as 1 gram equivalent. In a similar way, if it releases 1 mole of OH minus ion as a base, or it neutralizes 1 mole of H positive ion as base, then it will be considered as a maybe some problem is coming, and this problem is actually coming repeatedly. So probably, hopefully, it will not come onwards. Otherwise, I'll have to speak with the technical team of ours. We have received a call from the technical team. Hello. यार ये repeatedly हो रहा है, repeatedly सामने. So don't worry everybody, just allow us a few seconds and I think our issue will be resolved very soon. I have asked our technical support team to come and resolve the issue. So hopefully they are working on it and it won't be repeated from here. Anyways, let me continue until then. So what we are right now having is definition of 1 gram equivalent. So if talking about terms of acid or base, so wherever we can get 1 mole of H positive, 1 mole of OH minus ion, we consider as a gram equivalent. So let me give you one example. So there we have